Okay, hello everybody. Today we will be talking about velocity and acceleration. Basically, in physics, it's highly significant to know what the difference of velocity and acceleration is. For example, can you tell me everything you know about this object? If its acceleration is moving to the right, can you tell me where the object is moving? If you say the object is moving to the right, you are wrong because the object could be moving to the left, and the acceleration could be making it slow down. So basically, the acceleration does not determine the direction of an object or its velocity. The velocity is independent of the acceleration. But 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 if an object is if an object is accelerate if this object, let's say object A, is accelerating to the right for a long period of time, the object will eventually move to the right. That is, and then the interval between the change in velocity, so the time between the object, like for example the object is was moving to the left, so the interval when the object doesn't move to the left or to the right, its velocity equals 0. So anytime an object changes direction, the time between the object changes direction, the instantaneous velocity at that time is 0. For example, if an object is moving to the right and then it suddenly changes direction to the left, the time between the object moves to the right, the time between the object like moves to the left and to the right, the velocity equals 0. Uh, okay, but what if you have another mass and it's moving to the right, and then that's the direction of the velocity, and then the acceleration is pointing up. This acceleration changes the velocity's direction, but not magnitude. So the magnitude of the speed, the magnitude of the velocity is still the same, which is the speed. The speed is still kept constant, but this perpendicular acceleration changes the object's direction. So what we can say about this object is that whatever the acceleration or the net force is not doing any work on the object that's moving to the right. So let's say if you have this object and it's moving to the right, and then let's say the acceleration always points, like the net force always points in the direction of the acceleration. So if this is the net force and it's perpendicular to the velocity of the object, the work done on the object is 0. So let's get a gist of when you have conservation of energy. So when do you have conservation of energy? You have conservation of energy either when the work done by the non-conservative forces are equal to 0. So for example, if you have so let's say you have like this type of roller coaster, and then you have this object and it's moving around this roller coaster. First, the forces acting on this object is gravity, the force due to gravity, which is a conservative force, and the normal force, which is points perpendicular to the surface at every single time. So at this time, so at this instance in time, the normal force points perpendicular to the surface, and the force due to gravity always points down. So since at every single instantaneous position, at every single position of this block, the velocity is always perpendicular to the normal force, and the normal force is a non-conservative force, the work done by the normal force on this object is 0. So, and we also know that the work done by any non-conservative force equals the change in energy, So, so if the work done by a non-conservative force equals 0, if the work done by a non-conservative force equals 0, then you have conservation of energy. But we already know that gravitational force is a conservative force, so we can't add the force of gravity here. So we say that when the non-conservative work equals 0, you have conservation of energy. So energy initial equals energy final. Okay. And so let's analyze the block at this position. So at this position, the normal force points down. The gravitational force points down. And this object is going around in a circle. So we know that if the object is accelerating at a certain be quiet. So if this object is, let's say, these forces make the object's acceleration point toward the center. So if the object's acceleration is pointing toward the center for a long period of time, then the object will eventually fall. But if the velocity is high enough, then the object won't point in the direction of the acceleration. It would take longer for the object to point in the direction of the acceleration. And then the object is not going to stay at this position for a long period of time anyways. So that since it won't be at this position for a long period of time, it would eventually go around in a complete circle. So and we know that for rotational motion, that sigma fc equals mv squared over r. So if this is greater than or less than the normal force plus the gravitational force at this instance of time, then the object will go around in a complete circle. And then to get a more clear gist of this, you could say, to get a clear more gist of this, of why when an object has a really high velocity, it won't point in the, like, if the object's velocity is not high enough, the object wouldn't take a long time for it to go in the direction of the acceleration. Like, for example, we know the equation. We're all familiar with the equation. We're all familiar with the equation V B F equals B I plus AT. So let's say the initial velocity is positive 1 meters per second. Let's say in the positive x direction, whatever you choose that to be. And let's say that the magnitude of the acceleration is anti-parallel to it, and it's, let's say, 5 meters per second. And let's say the final velocity of the object is 0. No. And let's say, forget about the final velocity. Let's say the final velocity of the object is not 0. And then let's say for 2 seconds. So for 2 seconds, the object's final velocity would be negative 9 meters per second. So So for less than 2 seconds, the object's velocity is already pointing in the direction of the acceleration. Oh, that's not 2